So let's think about Scooter, our intern, again, because he's going to tell us, he's going to let us know about the mean value theorem. He was in the company car, and he's driving from Albuquerque. He started out right on the north side of Albuquerque, and drove up I-25, which I'm going to picture as straight north-south, not really. And he got to the south side of Santa Fe. And let's say that's 50 miles. It's pretty close. Let's say it's 50 miles exactly. And we wanted him to go to Santa Fe, so we were happy about that. But the mistake he made was he called us right as he was leaving, told us when he was leaving, and that was 12 noon. And then he called us right when he got here, and said, "Hey, I'm at the south side of Santa Fe. Aren't you proud of me that I got here?" And he called it. That was at 12:30. And we said, "Wait a minute, Scooter. That's really suspicious because we can calculate your overall, or as it's usually known, average velocity. That's 50 miles over 1/2 an hour. That's 100 miles per hour. We told you not to speed anymore, Scooter, but that's way over the 75-mile-an-hour speed limit." And Scooter's like, "No. Really, I wasn't speeding. Really, I wasn't." And we say, "Well, Scooter, let's think about mathematically what you're telling us. Let's say here's t equals 12, and here's 12.5, and here's a picture of where you were. You're at the north side of Albuquerque, and then here's the south side of Santa Fe. That's 50 units. That's 1/2, so that's 50 miles. That's 1/2 an hour. And we don't know exactly what your function, s as a function of t, is, but we know that here's the secant line. And we're not going to believe you if you say that your tangent slope," he might claim, Scooter, as a last-ditch attempt, he might say, "But I know you guys know calculus. What you care about is v of t equals s prime of t, the instantaneous velocity. Sure, my average velocity was 100 miles an hour, but I claim there was no point at which I was going over 100 miles per hour. Or over 75 miles per hour. I claim I was not speeding." And we just laugh. And we say, there's no way. If you were always going under 75 miles an hour, how could you have that average? And a way to say that more precisely is to say, well, look what his graph could have been. He could have started slow and then ended up really fast. Well, then certainly there's part of that that's much steeper than this dotted line. He could have started out fast and gotten slow, or he could have wiggled in all kinds of ways. But there's definitely going to be places where he's going that magic number of 100 miles an hour. And the mean value, this is what the mean value theorem says. One of the versions of it says that if you draw a line parallel to that tangent, there's going to be that secant slope. That guy's the secant slope, the overall velocity. There's going to be some tangent slope that equals that secant slope. So not only can we say he was speeding, he was going well over 75, we can say there must have been at least one instant, maybe more, when he was going exactly 100 miles an hour. Where if he had glanced down at his speedometer, it would have read exactly 100. And that's what the mean value theorem says. So MVT, I'm going to fill it out with one big blank in it. Let F be blank, and that's going to be one of these theoretical assumptions that we need to make the thing work, and we'll talk about that in a second. Let's see, blank on the interval AB. Then there is some C in AB such that f prime of C equals, and now this is like Rolle's theorem, but this is the part that's a little more complicated. That's the secant slope. So it says take some interval, look at f of a and f of b, calculate the secant slope, then there must be, so that's this guy, just calculate that number. That's easy. You just do that right off the bat for most mean value theorem problems. Then there must be some magic number c in the middle, or maybe more than one, where the tangent slope, that's f prime of c, is equal to the secant slope, where these lines are parallel. Now let's see if we can fill in the blank. What has to be true? I should have done this a little better. We're going to have to modify this a little bit as well. So we're looking at this interval AB, and it's the same kind of thing as for Rolle's theorem. How could we cheat? How could Scooter theoretically cheat? Well, here's one way. He could teleport. Like, he's going along, he's just sitting in the Starbucks in Albuquerque, and then boom, he's suddenly in Santa Fe. There's certainly no point in this interval that has any non-zero slope at all, and suddenly he's there. Okay, so that would be if it was discontinuous. So it's our usual thing. If you allow teleporting cars, you can get around all of these theorems. But there's another way you could cheat. If he wants to claim, okay, I admit I was speeding, but I object to your claim that I could have looked down at my speedometer and saw exactly 100 miles per hour at some point. I could have been sitting in the coffee shop and then gone tremendously fast, 300 miles an hour, 1,000 miles an hour, to get to Santa Fe. Well, we'd say, nope, that's a sharp corner. That would be if you allowed your function to be not differentiable. We already talked about what this, in the context of Rolle's theorem, we talked about what this means. It means infinite acceleration. He'd be squashed into jelly at that instant. Okay. So the complete version of MBT is let f be continuous. It's exactly the same as Rolle's theorem on the whole interval, no teleporting ever, and differentiable. And it turns out, to get the strongest version of the theorem, you don't actually need to check the differentiability right on the endpoints. Okay, so let's scratch that, because there's a little bit of a subtlety that you need continuous on the whole interval, including the endpoints, and differentiable all the way, but not necessarily including the endpoints. It's a pretty minor technicality, to be honest. The main thing is this idea that if you're going from here to here, draw that dotted line, there's got to be somewhere in between where the slope is equal to that. So the problems that we have in the book, some of the problems are very much like what we were doing for Rolle's theorem. So let me stop this one here and do another real short video doing one problem like that to see how the actual problems work that you're going to do.